The first technique is air suspension. Here the basic principle is to disperse the solid core material in a supporting air stream and spray coating material on air suspended particle. Means what? Here the particle are in a hanging condition. Particle are in a hanging condition. So the sufficient air is passed from the bottom to hang the material. Hang the material. So here the all the solid material or the liquid they are suspended, remaining suspended with the help of air. The method, the particles are suspended on an upward moving air stream. As each pass through the coating zone, the core receive an increment of the coating material. As the particles are passed through the coating zone, they receive the coating material on a core. On a core. That means the core receive the coating material layer by layer and increasing the thickness as per need. That is more thickness, less thickness, or intermediate thickness. That cyclic process is repeated several hundred times depending upon the coating thickness desired. And the supporting air stream that is served to dry the product while it is being encapsulated, right? So these are the equipment here. That is a nozzle. From the nozzle the spraying liquid is passed from the bottom, and here the particle are remain suspended, right? Okay, then factor which affect on the encapsulation. So which are the factor which is critical during the encapsulation process. During the encapsulation process, the coating material concentration. If the coating material concentration is very thick, then it is unable to pass through the nozzle. If the coating material is very thin, then the material is not stick on the particle very well. So the concentration of coating material is optimum, not too much thick and not too much thin. It is intermediate. The coating material application rate, that is critical parameter. Coating material application rate, it is a coating, it is a critical parameter. So when you apply first time, you find out the rate of coating material application rate, then you adjust it. The volume of air required to support the core material, these are the critical parameters. Sufficient quantity of air is passed from the bottom to support the particle core into the hanging condition. The amount of coating material required, amount of coating material required. So which type of coating material is required and amount, how much amount of coating material is required, both are the critical parameter, right? So you should calculate before trying starting of the coating process. Inlet and outlet operating temperature. So sufficient temperature are required to uh, maintain the temperature for drying purpose. So inlet and outlet both are adjusted during the coating operation, right? Then the drug property, that is core materials property, that is density, surface area, melting point, solubility, friability, volatility, crystallinity, and flowability of the core material is find out before starting off the coating process. These are the critical parameter and the property required for the microencapsulation process. The second is the conservation phase separation. So yeah, that is main three step. If you apply the conservation phase separation technique, the main three step. The first step is formation of three miscible phase. Second is the deposition, and third is the rigidization of the coating. So what is requirement of three miscible liquid? Deposition of coating and rigidization of coating. Right? So that is represented by a flow diagram. The three phase, that is one is the polymer, second is the core, and third is the liquid. Three phase, that is polymer, core, and liquid. Then mix all that phase, three phase, and to prepare the formation of three miscible phase. And here the phase separation is done by the various techniques which are discussed below, right? Which are the various techniques. So by utilizing this 6 to 7 techniques, that phase separation is done. After that phase separation, the polymer which is deposited on the core means what? Drug. Core means drug. So here the polymer which is deposited on the drug, that is rigidized with the help of different techniques, that is cross-linking, dissolution, and thermal techniques. Then finally you obtain the microencapsulation. Microencapsulation means the inner side is the drug and outer side the polymer coating you obtain. And what is the need we are discussing in the previous, what is the advantage disadvantage of microencapsulation? So in that, that is prevent from the environment, right? Here the phase separation. So the in the first step, if you see here in the first step, the phase separation is done by the various techniques. Which are the techniques? These are the techniques: the temperature change method, that is incompatible polymer addition, non-solvent addition, salt addition, solvent evaporation techniques, and polymer-polymer interaction. So one by one we are discussing the temperature change. How we separate phase are separate out. Phase means what? You know, the solid and liquid and liquid, immiscible liquid. So when you identify these are the separate phase, you see the two layer, then you easily say these are the two phase. If it is mixed each other very homogeneously and you cannot identify the separation, then it is called as a homogeneous mixture. But if you find out the two layer, then it is called as a phase, right? So how we separate this phase? So the, you know, the phenol water system, same theory are apply here. The one side, that is temperature, and other side is the polymer concentration. And here the temperature play a important role. Temperature play a important role. So that above that points, that is A, the polymer and the solvent are mixed with each other uniformly. So you are not separate out this polymer. But below this layer, that is here, separation is occur. Right? So here the figure show a general temperature composition phase diagram for the binary system composed of polymer and solvent. Here the binary system, you know, the phenol water system, that is binary system. So same principle are apply here, but here instead of phenol, we are use the polymer. So polymer and solvent. Polymer and solvent. Solvent is that is polar or semi-polar, right? The other system having an overall composition represented as the point X on abscissa, that is x-axis, right? X-axis. The composition of polymer are indicated. Exists as single phase On x-axis it is single phase. Homogeneous solution at all the points above the phase boundary or binodial curve, that is EFG. Homogeneous solution. Homogeneous solution that is exist as a single phase, right? And homogeneous solution at all the point above the phase boundary or the binodial curve EFG, sorry, FEG is the one phase system. On that boundary and above that, that is one phase system. And the temperature of the system is decreased from the point A along the arrow line, that is AEB. The phase boundary is cross at point E, cross at point E, and the two phase region is entered. And as the line is indicating arrow at the bottom side, that is below the boundary FEG, that is two phase system is obtained. If you see here AEB, so here the two phase system, on that line or above that one phase system, means you cannot separate the polymer and solvent, but here these are the separation of polymer and solvent are obtained. The phase separation of dissolved polymer occur in the form of immiscible liquid droplet. If a pore material is present in the solvent, under the proper polymer concentration, the temperature and agitation condition, the liquid polymer droplet coating around the dispersed coat particle and thus the forming the embryonic microencapsulation. Here if you increase the temperature, proper polymer concentration you have, then agitation condition you are maintained, then what happening, the liquid polymer droplet coating. So here the drug which is dissolved in the solvent, they are converted into a droplet and the polymer are coated that droplet. The polymer are coated that droplet and you obtain the dispersed core particle. Core particle means drug. You obtain the core particle and thus the forming the embryonic microencapsulation. So by that way you obtain the microencapsulation. So to explain very well by uh, taking this example, here the coat means the polymer is the ethyl cellulose, coat polymer is the ethyl cellulose, core means the drug is paracetamol and the solvent is cyclohexane. The first ethyl cellulose is suspended in the cyclohexane, so the polymer is dissolved in cyclohexane. Slowly increase the temperature 50 to 60 degree. Ethyl cellulose is solubilized, then disperse paracetamol. If the ethyl cellulose is solubilized in solvent, that ethyl cellulose is the polymer that is dissolved in solvent. Then add the drug, that is core. So that drug is also dissolved. There are two phase. That is solution of ethyl cellulose and drug. But actually it is three phase. But ethyl cellulose is soluble in the solvent. That's why it is not separate out. So you have a phase is two. That is solution of ethyl cellulose and TCM. Right? These are the two phase. Then slowly cool the mixture. If you decrease the temperature, again that ethyl cellulose which is dissolved at higher temperature, they are precipitate out or they are coming out from the system. So that is converted into the three-phase system. So what happening at that time? That core, that drug particle, which is dispersed in the ethyl cellulose solution, that is remain inside. The parastamol is remain inside, and outer side that ethyl cellulose are coated. Outer side the ethyl cellulose are coated, and you obtain the microencapsulation. The second technique is the incompatible polymer addition. Incompatible polymer addition, right? So here what we should do? So add the another polymer which is not soluble. Add the another polymer, right? So here the liquid phase separation of the polymeric coating material. Liquid phase separation of the polymeric coating material and microencapsulation can be accomplished by utilizing the incompatible polymer. Incompatible polymer. So by taking the example, for example, coat is the ethyl cellulose, same polymer, ethyl cellulose, vehicle is the toluene, core drug is the methylene blue hydrochloride. Incompatible polymer, that is liquid polybutadiene. Liquid polybutadiene is the incompatible polymer. Right? Liquid polybutadiene is the quite soluble in toluene. It is not soluble. Quite soluble in toluene. Incompatible with ethyl cellulose. Incompatible with ethyl cellulose. So when we dissolve the butadiene, that is dissolve more, and ethyl cellulose they are precipitate out. They are precipitate out. The liquid polybutadiene disperse the ethyl cellulose from the toluene subsequent microencapsulation. So first what we should do, so in vehicle we dissolve the drug and ethyl cellulose. So firstly the ethyl cellulose are dissolved with the drug in toluene. So you obtain very clear solution. But when you add the incompatible polymer, that polymer are dissolved more as compared to ethyl cellulose. So the ethyl cellulose want to outcome from the system. So they are quoted that ethyl cellulose, how they outcome from the system, try to outcome from system. So here the more soluble they are displace the ethyl cellulose, take part the role of ethyl cellulose. So here the ethyl cellulose are outcome from the toluene by coating on the core, coating on the core. Next technique is the non-solvent addition. Non-solvent addition. હવે આપણે in that case, instead of polymer, we add the solvent which is not soluble. So here the two solvent, one polymer, one drug. A liquid that is non-solvent for a given polymer can be added to a non-solvent addition, in that a liquid that is non-solvent for a given polymer, non-solvent for a given polymer can be added to a solution of the polymer to induce the phase separation. For example, here the coat material, that is polymer, is the cellulose acetate butyrate. The core, that is drug, is methyl scopolamine hydrobromide. Vehicle is the methyl ethyl ketone, and non-solvent is the isopropyl ether. Then how we obtain the microencapsulation? So here the polymer is dissolved in methyl ethyl ketone. To it, micronized methyl scopolamide hydrobromide is added. Dispersed with stirring. So you obtain very soluble solution. Right? The resulting mixture is heated 55 degrees Celsius. So The drug and polymer that is very mixed or soluble in methyl ethyl ketone. But when you add the isopropyl ether, is added slowly to check the phase separation. Then subsequent microencapsulation fall is obtained. So when you add the non-solvent, then what happening that both solvent are mixed, but that core and coat material are not soluble in isopropyl alcohol. So that is coming out from the system. That is coming out from the system. The next method is the salt addition. Already you know that common salt process. You already know that things. Salt addition. The soluble inorganic salt can be added to a aqueous solution of the certain water-soluble polymer to cause the phase separation. Inorganic solvent, right? When you add to a aqueous solution of certain water-soluble polymer, this is the phase separation. Here the gelatin is the water-soluble polymer. Coat, coat is the gelatin. Core, drug is the vitamin A, oil-soluble vitamin A. The vehicle is the corn oil, right? And salt is the Na2SO4. So we are understand the method, right? In that the oil soluble vitamin is dissolved in corn oil. So like dissolve like here you know that is oil is soluble in oil. That is non-polar is dissolved in non-polar. Polar is dissolved in polar like that. Here the vitamin A that is oil soluble vitamin. So always use the vehicle oil. Then is emulsifying to desired drop size, that is 10% solution of high quality gelatin to 50 degrees Celsius. So add the gelatin. That gelatin is the emulsifying agent, right? So you obtain the very well mixed solution. Then slowly add the 20% solution of Na2SO4 with the continuous stirring. So that the salt, when you add that salt, the gelatin become the harder. Because of that salt, the gelatin become the harder and decrease the solubility of gelatin. This result in the encapsulation of the oil globules with the uniform coating of gelatin. So the previously before adding of that Na2SO4, the gelatin is solubilized. That is working as a emulsifying agent. So you obtain very well mixture or emulsion of with dog oil and emulsifying agent. You obtain very well mix that quantity. But when you add the Na2SO4, that salt become or convert that gelatin into the harder property. When you add any salt in the gelatin, sulfate salt, that have a property to decrease the gelatin solubility. And because of cross-linking, that is behind that is the theory of cross-linking, right? So because of that, cross-linking of gelatin is decrease the solubility. They are coming out from the system by coating the drug with gelatin. So inner side is the vitamin A and outer side is the gelatin. That is called as a salt addition techniques. Then next step technique is the solvent evaporation technique. So very widely used this technique in the laboratory, solvent evaporation technique. So here mostly we are used of volatile solvent. The coating polymer is dispersed in a volatile solvent. Coating polymer is dissolved. Polymer is dissolved in volatile solvent, which is miscible with the liquid manufacturing vehicle, which is miscible in liquid manufacturing vehicle, right? The core material drug is also dissolved in the coating polymer solution. So volatile solvent you take in that polymer and drug both are solubilized. With agitation, the core material mix is dispersed in a liquid manufacturing vehicle fit to obtain the appropriate size microcapsule. To obtain the appropriate size microcapsule. This mixture is then heated to operate the solvent for the. This mixture is then heated to operate the solvent for the polymer. That polymer shrink around the core. That polymer shrink around the core. The core material may be water soluble or water insoluble. The core material is water soluble or water insoluble. Right? So what happens? Only the simple technique are apply here. You are take the isopropyl alcohol, that is volatile solvent in that add the polymer and drug, that is very well dissolved. Drug and polymer both are suitable. You select the suitable solvent, right? At that time, you select the suitable solvent. So the solvent selection is depending on the nature of drug and polymer. Which polymer you are used and which drug you are used. Depending on that, you select the volatile solvent. In that, both are soluble. Apply the heat, solvent is evaporated, and you obtain the inner side drug, outer side polymer. Simple techniques, right? Because as the solvent is evaporated, the remaining amount is the solid, which is remaining in the container, that is drug and polymer. The solid molecule are not evaporated, only solvent molecule are evaporated. Right? The solvent is removed from the system, but the solid, that is polymer and drug, which is remain inside. So at that time, the polymer are coated the drug, that is core material. Polymer-polymer interaction. Polymer-polymer interaction. In that, the interaction of the oppositely charged polyelectrolytes. The oppositely charged polyelectrolytes can result in the formation of the complex having a such reduce the solubility that phase separation occurs. So when that complex are formed, that decrease the solubility, and because of the decreasing the solubility, the that sol one phase system is converted to a two phase system, right? Or the polymer are exist out from the system. The aqueous solution of gum arabica and gelatin are prepared. The aqueous solution of gum arabica and gelatin are prepared. Then both polymer solution are mixed together in equal amount. Then methyl salicylate is added. Methyl salicylate is our drug, right? The we are added methyl salicylate in that polymer. Then dilute to above twice their volume with water. Dilute the content with water. Adjust the pH 4.5 and warm to 40 degrees Celsius. Finally, cool the solution to 25 degrees Celsius and 10 degrees Celsius. So the phase separation are done. So here, when you decrease the temperature, that polymer, that is gelatin and gum arabica, they interact with each other and they form a complex and they are converted into the insoluble. So previously when you apply the warm 40 degrees Celsius at that time they are soluble. But as you decrease the temperature, they are converted into the insoluble, or they make a complex, that polymer form a complex, and that complex decrease the solubility, so they are coming out from the system with coating on the methyl cellulose. Methyl cellulose is the drug, so they form a coat on the methyl cellulose. Right? Release mechanism from the microencapsulation. So here you know that reservoir, the inner side is the drug and the outer side is the polymer. So when you dissolve it, they create a pore, they create a spore, and because of that creating pore, the drug is released out from the pore channel, that is hydrogen plus drug. The drug is released out from the drug reservoir. As the time is going on, the drug is released out from the. Okay, so application of microencapsulation. The first application is sustained release or prolonged release of medication. First application is sustained release or prolonged release application. The second is the taste masking of medicine. If the drug is bitter in taste, then done the coating on the drug. Taste masking is the application. The third application is the prevent incompatibility. If the two drugs they are incompatible with each other, then prepare the microencapsulation and fill in a one container, one capsule. So there is no problem. So to prevent the incompatibility. Increase the stability. So here the external factor, if the moisture, oxygen, then the external factor they are affect on the drug, then the drug is converted into the encapsulation, then increase the stability. Drug which can liquid at the room temperature and undergo the oxidation can be microencapsulated, that is vitamin A. So here the drug which is undergo oxidation, that is degradation process. So convert that into the microencapsulation. So here the vitamin A is converted into the capsule by microencapsulation technique to prevent the degradation, oxygen degradation, right? The protect against the atmospheric moisture and other reaction. To protect against the atmospheric moisture and other reaction. Uh, so here the external environment, that is moisture and any other external factor, they are protected by converting into the microencapsulation. Protect against the side effect like the gastric irritation, for example KCl. So here the drug they create the gastric irritation, the drug which create the gastric irritation, that is coated, for example, KCl, they are coated with the particular polymer to prevent gastric irritation. To reduce the volatility of the drug, if the drug is volatile in nature, for example, methyl salicylate, that is in a liquid form, then it is coated with the polymer to decrease the volatility. To decrease the volatility. To improve the shelf life. To improve the shelf life. So if the any drug which is coated with the polymer, then that drug are remain safe for longer period of time. So increase the cell life. Right?